Space is vast, bigger than vast, really. It's filled with incredible wonders, things that make your brain hurt just trying to think about them. But of all the cosmic curiosities out there, few capture the imagination quite like black holes. These celestial objects are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where the very fabric of our universe is stretched to its breaking point, a place where the laws of physics as we know them cease to apply. That's a black hole. Black holes are the remnants of collapsed stars, their immense gravity warping the fabric of space-time around them. They're invisible to the naked eye, shrouded in a veil of mystery that continues to fascinate scientists and stargazers alike. For decades, they were the stuff of science fiction, but today, we know they're very real. Join me, and let's journey together into the heart of these cosmic enigmas. Imagine a giant cosmic vacuum cleaner sucking up everything in its path. That's kind of what a black hole is, but instead of air, it's sucking up light and matter. A black hole is a region of space-time where gravity is so powerful that nothing, not even light, can escape its pull. It's like a cosmic trapdoor. Once you cross the threshold, there's no coming back. This threshold is known as the event horizon, and it's the point of no return. Once you cross the event horizon, you're destined to be pulled towards the singularity at the center of the black hole. But what exactly is a singularity? It's a point of infinite density, where all the matter that ever fell into the black hole is compressed into an infinitely small point. It's a mind-bending concept and one that we're still trying to fully understand. Let's imagine for a moment that you could survive a trip into a black hole. What would you see? What would you experience? As you approach the black hole, you'd start to notice the effects of its immense gravity. Time would slow down for you relative to someone observing from a safe distance. You'd also experience spaghettification, a rather unpleasant process where the intense gravity of the black hole stretches you out like a noodle. As you get closer to the singularity, the curvature of spacetime would become more and more extreme. Light itself would be bent and distorted, creating a kaleidoscope of warped images. Finally, you'd reach the singularity, the point of no return. Here, all matter is compressed into an infinitely small point, and the laws of physics as we know them break down. What happens beyond this point is anyone's guess. Some theories suggest that you might emerge into another universe, while others propose that you'd simply be crushed out of existence. Black holes are more common than you might think. In fact, astronomers estimate that our galaxy alone could contain millions, even billions of these enigmatic objects. These black holes come in a variety of sizes, from stellar mass black holes which form when massive stars collapse at the end of their lives, to supermassive black holes which lurk at the centers of most galaxies, including our own Milky Way. Supermassive black holes are truly colossal, with masses ranging from millions to billions of times greater than our Sun. These behemoths are thought to play a crucial role in the evolution of galaxies, their immense gravity influencing the formation of stars and the dynamics of galactic disks. The sheer number of black holes scattered throughout the universe is a testament to the power of gravity and the incredible forces at play in the cosmos. Section 5: Spaghettification and Beyond. The ultimate fate? The idea of spaghettification is a popular one, and for good reason. It's a gruesome thought being stretched and compressed by the immense gravity of a black hole. But what does the science actually say? As you approach a black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head. This difference in gravitational force would cause you to be stretched out, like a piece of spaghetti being pulled from both ends. But don't worry, you wouldn't survive long enough to experience the full effects of spaghettification. The intense radiation surrounding the black hole would likely fry you long before you got close enough to be stretched. So, what happens to the matter that falls into a black hole? It's added to the black hole's mass, increasing its size and gravitational pull. In this way, black holes grow bigger over time, consuming anything that ventures too close. Section 6: Stellar Graveyards, the birth of a black hole. Black holes are born from the death throes of massive stars. Stars are like cosmic pressure cookers, fusing hydrogen into helium in their cores, and releasing a tremendous amount of energy in the process. This outward pressure from nuclear fusion balances the inward pull of gravity, keeping the star stable for millions or even billions of years. But eventually the star runs out of fuel, and the outward pressure ceases. When this happens, gravity takes over, and the star's core collapses in on itself. For stars much more massive than our Sun, this collapse is so violent that it creates a black hole. The outer layers of the star are blasted off in a supernova explosion, one of the most luminous events in the universe. Meanwhile, the core continues to collapse until it becomes infinitely dense, forming a singularity at the heart of the newly born black hole. Section 7. Supermassive giants reigning over galaxies. While stellar mass black holes are impressive in their own right, they pale in comparison to the supermassive giants that lurk at the centers of most galaxies. These behemoths can have masses billions of times greater than our Sun, and their gravitational influence shapes the galaxies around them. How do these supermassive black holes form? That's a question that astronomers are still trying to answer definitively. One theory is that they form through the mergers of smaller black holes over billions of years. Another possibility is that they formed in the early universe from the collapse of massive gas clouds. Regardless of their origin, these supermassive black holes play a crucial role in the evolution of galaxies. Their immense gravity can drive star formation, and they can also regulate the growth of their host galaxies by gobbling up gas and stars that venture too close. Section 8. Hawking's Revelation. Black holes aren't so black after all. For decades, black holes were thought to be completely inescapable, their gravity so strong that nothing could escape their clutches. But in the 1970s, physicist Stephen Hawking made a groundbreaking discovery that changed our understanding of these enigmatic objects. Hawking showed that black holes aren't entirely black after all. Due to quantum mechanical effects near the event horizon, black holes emit a faint thermal radiation, now known as Hawking radiation. This radiation carries away energy from the black hole, causing it to slowly evaporate over time. The rate of evaporation is incredibly slow, especially for large black holes. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely. Section 9. The evaporation of a black hole, a universe-ending event. The evaporation of a black hole is a mind-boggling concept. As a black hole shrinks, the rate of Hawking radiation increases, leading to a runaway effect where the black hole eventually explodes in a burst of energy. This explosion would release all the matter and energy that the black hole had consumed over its lifetime, potentially creating a spectacular cosmic fireworks display. While the evaporation of a single black hole is unlikely to have a significant impact on the universe as a whole, the fate of all black holes is intimately tied to the ultimate fate of the universe itself. Some cosmological models predict that, in the distant future, all matter in the universe will be consumed by black holes, and these black holes will then slowly evaporate away, leaving behind a vast and empty universe. Section 10. Black holes and time travel, fact or fiction. Black holes have long been a source of fascination for science fiction writers, and for good reason. Their immense gravity and enigmatic nature make them ideal fodder for stories about time travel, wormholes, and other mind-bending concepts. But what does science have to say about the possibility of using black holes for time travel? While the equations of general relativity do allow for the possibility of time travel through wormholes and other exotic space-time geometries, these solutions are highly speculative and rely on conditions that are unlikely to exist in the real universe. For example, creating a wormhole would require the existence of exotic matter with negative mass energy density, something that has never been observed. While it's fun to speculate about the possibilities, the reality is that using black holes for time travel is likely to remain firmly in the realm of science fiction for the foreseeable future. Section 11. Conclusion. Mysteries of the cosmos. Black holes, once relegated to the realm of science fiction, have emerged as one of the most intriguing and enigmatic objects in our universe. From their mind-boggling density to their ability to warp space-time, black holes continue to challenge our understanding of the cosmos. While we've learned a great deal about black holes in recent decades, many mysteries remain. How do supermassive black holes form? What happens inside a black hole? Can we harness the power of black holes for our own purposes? These are just a few of the questions that continue to drive scientific inquiry. As we continue to explore the universe, black holes are sure to remain at the forefront of our cosmic curiosity, beckoning us to unravel their secrets and unlock the mysteries of the universe.